Okay, so we have a question here where we've been given a formula, Q is equal to e to the power of minus 0.693 over 5730 t. And in this formula, Q stands for the proportion of what's called carbon 14 that's left in an item. So percentage, let's say, or proportion of carbon 14. So Q stands for the percentage or proportion of carbon 14 left in an item, where T represents the age of the item. So if we know the age of an item, let's say that's been found in an archaeological dig, we put that age in for T, and it will tell us what's the percentage of carbon 14 in the item. Now, ideally, this works the opposite way around. We'll find an item, we'll measure the percentage of carbon 14 in it, and we'll actually solve for T, which is what we're going to do in the second part of the question. And that way archaeologists can measure the age of items that they found. This formula could easily have been written in this format, so Q of T, so in function notation, Q of T equals e to the minus 0.693 over 5730. And if it was written like that, it might just help us understand a little bit more that the percentage of carbon that's left is dependent on the time. So Q is dependent on T. T is the only variable in the question. So we'll sub values in for T and we'll get percentages out. E isn't a variable. E is a constant. We know what E is. It's Euler's number and it's approximately 2.718. And so that isn't something we're trying to solve for in the question. That's a number that's in the question. Now, what we're trying to find is the age of an item that's 2,000 years old. So again, with my notation, I'd probably say the Q of 2000, so the proportion of carbon left after 2000 years is equal to e to the power of minus 0.693 bracket 2000 all over 5730. So we need to be careful with the calculator. Now, you might just see it written as Q equals that. It's the same thing. But when we throw this into the calculator, we get the number 0.7851. And so what that tells us is that after 2,000 years, the percentage of carbon 14 left in the item is 78.51%. So 78.51% of carbon 14 remains in the item. So that's a fairly straightforward inputs question. We've been given a formula, we input a value and we get out the percentage. So if we have a look at it again quickly here, we have our formula and it's simply a substitution question. We're going to put 2000 in for the T and then throw it into the calculator and we get 0.7851 or 78.51%. Second part of the question is going to be us trying to solve for T, the time. In this question, we're told that an item has been found and the percentage of carbon left in it is 0.3402, or we can say 34.02%. Now, the first thing to do in a question like this is do a bit of a common sense check. If 2,000 years, so if 2,000 years had 78.51% of the carbon left, well, to get to a stage where there's only 34.02% of the carbon left, well, that's going to be a much longer time than 2000. This is a much older item than the item that had 78.51% of the carbon left. So this is a logs question, so a logs equation. We're going to let the formula equal 0.3402. So the 0.3402, that's the Q. And then the only thing that we're trying to solve for is the T. So equals E to the minus 0.693 T over 5730. Now, there is only three pieces here. We have our answer or our argument. So this is our answer. We have our base of the power. And then, even though this is a fraction and has the variable in it, this is the exponent. So we have our three pieces, exponent. And we know that if we have something in index form, and if we're trying to solve for a letter that's in the exponent, we need to change that into logs form. So we can change that into logs form by looking in our tables, and we have that the log of y to base a is equal to x, and we can rearrange this to say a to the power of x equals y. So we can go from logs form to index form. So let's do that with the equation we have. So e becomes the base of a log, so log e. The 0.3402, that's the argument, so that goes there. And this is equal to minus 0.693t all over 5730. And we can see that the t is no longer in a power, and this is an equation that we're going to be able to solve. I'm trying to isolate the t, so what I would do is I would multiply both sides by 5730 and divide both sides by minus 0.693. So we have that t is equal to the log base e. Now log base e, just a note here on the side, we can write that if we wanted the natural log, ln, but we'll just keep it as log base e for the minute, 0.3402. I'm going to multiply both sides by 5,730, so 5,730. I'm going to divide both sides by minus 0.693, minus 0.693. I'm going to throw that into my calculator, and I get 8,915 years. So that's the age of the item that would have 34.02% carbon-14 left. Now, always be careful. The question says correct to two significant figures. So what we need to do is we need to just round this off to two significant figures. The two significant figures are the 8 and the 9, and then whatever digits are remaining are zeros. So that's to the nearest, let's say 100, 8,900 years. Okay, let's have a look at the type solution, just see was it done any differently. So again, I'm going to let q equal 0.3402, and I know I have to solve for t. I always say that if the t is in the power, well, that's going to be a logs equation. So here's our rule of logs. So we have our argument, 0.3402, we have our base e and our exponent, and then when we rearrange this, we have log 0.3402 to the base e is equal to minus 0.693 t over 5730. Now what I actually did was I divided both sides by this, and we get the same answer, 8,915, and if we correct that to two significant figures, that's 8,900 years.